this holds for everything in the universe. Everything in the universe follows the same set of instructions, including us. We're also stuff. And the very good thing is we have a very good idea about what these instructions are. It's that. That's the instructions. It's very complicated, but not too much. It fits in a page. But the instructions are a bit too complicated for us. We can't really carry them out in our heads. Okay, so we build synthetic universes, computers. The computers are a lot better than us at following these instructions, step by step. How do we know in the future, computer? Well, how can you not just carry out the instructions, human? So somewhere in the mind of the computer is a little universe. The computer is imagining a universe, and it's carrying out these steps. And we're looking at the computer, and the computer tells us what's going to happen in the future. It's a bit mysterious. Oftentimes, though, the actual law, the one on the left, is too complicated to carry out. Even the computers can't do it. It's that complicated. So then what we do is we simplify them. We say, oh, okay, we really don't need that bit in the box. We don't need this little bit in the bigger box and so on. We just need this and that. So we just sort of simplify it a little bit, and then we have these effective laws. So here's a few. That's a law for water swirling around the propeller blade. Here's a law for a falling apple. Here's a law for the sound of a trombone. So you can actually extract, you can squeeze out this big, complicated law, and you can extract these little, simpler laws. Now, I'm interested in the effective laws of life. Okay, so can I write an equation, something like, oh, horse equals 1/3 times more horse squared. Okay, can I write down something like that, and can I explain life that way? That's what I would like to do. And I would like to know what exactly is it about the physical laws that gives rise to life. Okay, so is it, do we need to have gravity to have life? Do we need to have energy conservation in order to have life? Do we need, I don't know, do we need to have a sun? Which one of these bits of the universe are necessary? And which bits are sort of, okay, they're okay, they don't hurt. They can be there, but they don't really play a crucial, essential role for life to exist. And in order to answer this question, again, we go to our computers, we build these synthetic universes, and we ask, okay, what's the simplest ingredients? What's the least amount of ingredients that I can program into the computer so that it evaluates these instructions, it follows these instructions, and it produces things that look like life. And I'm going to show two of them to you. No, I'm just going to show one of them because time is a little bit limited here. I'm going to show you a video. Where's my video? Okay, so this is called the Gray-Scott reaction. The way it works is in this universe, there's only two kinds of substances, U and V. They're letters. And in this universe, these letters undergo a chemical reaction. Whenever 2U combines with a V, it produces 3U, whatever. Just one reaction. You add U's, you remove V's. You add U's, you remove V's. So 3 laws, okay? You add stuff, you remove stuff, and there's a chemical reaction. And this is what comes out. Oh, okay. That looks familiar. That looks like cells dividing. So, yes indeed, with very minimal laws like this, you can achieve self-replication. You need to add a little bit more to obtain other things like evolution or things eating each other. Okay, so another very popular example is the Conway's game of life. Yeah, why not? This is what it looks like. So in this case, the rules, there are 3 rules. There's a square grid, and the little squares get to be black and white, let's say. And if a black square has too many neighbors, or it's too crowded, the black square dies and becomes white. If it has 2 neighbors, too little neighbors, oh, it's too lonely, it dies also. If it has exactly 3 or 4 neighbors, then oh, that's good. It remains. It remains to be alive. If there's a white square and there's few neighbors around the white square, oh, that's also good. White turns into black. Okay, these are the rules. And this is what comes out. This is called game of life. This is the sort of things that you see. That's my daughter. See, so you have these self-replicating features. It produces those little things. Okay. Now you might be asking, is this a game? Is this a computer game? Is this philosophy? Is this theology? Well, it's kind of all those things. There's a little cartoon. Oh, synthetic life sounds hypothetical and useless. And then the professor says, oh, this evolved in my computer, and it doesn't scratch furniture. So, you know, the cat might get replaced. But no, this is actually a very practical thing at the same time. You can use these ideas in engineering. You can, for example, design an antenna. What you do is you build a universe with funny laws. In this weird universe, there are 3 laws. The first law is that antennas can make babies. That's strange, but okay. I mean, it's my universe. I do whatever I want in the computer. Antennas make other little antennas. Law number 2. Antennas do exactly what antennas do in our universe. We know how antennas work, like physics, okay? So we just code that in. Law number 3. The survival of an antenna depends on how well it functions. Okay? So antennas make babies. All antennas do exactly what real antennas do, but I kill them if they're not good antennas. And I let them live if they are good antennas. Okay? And I just repeat this process for millions of generations. I let the antennas evolve in my computer. I patiently wait for millions of years, which is a second in my computer. And then something evolves. I see it in the computer. I just go out and build it. I build exactly the same thing that I see in the computer. What comes out? Perfection. This is what comes out. And this went to space in 2007. This is NASA's genetically designed genetic algorithm antenna. And look at how strange it looks. A human engineer would not come up with this weird shape, but evolution does, and it works perfectly. Okay, so this went to space. So I'm going to talk a little bit about my own research. So far everything when I was like, okay, philosophy, yada yada. So what do I do when I go to my office? I build these models in order to understand how complexity evolved, and in particular I'm interested in how social behavior evolved. So the question is, you start with these little microbes. Oh, the little microbes come together somehow. Okay, so you put a bunch of microbes maybe in a puddle, you wait for a couple million years, you come back, and you see a rainforest or something. Okay, so how do the bacteria become interdependent? How do they form these multicellular organisms? How do multicellular organisms start depending on each other to form ecosystems? So how come, what's the mechanism behind the buildup in complexity? That's the question that I'm interested in. And I would like to know what's the role of the physical laws in this process. Okay, so as I said in the beginning, do I need the sun? Do I need gravity? Do I need, I don't know, F equals ma? Do I need falling apples? Which of those things exactly is it that gives rise to complexity? And you might think, well, of course, it's all survival of the fittest. After all, we became faster and smarter, and horses became bigger and stronger. Surely little things are going to come together and form these bigger, more complex things. But the answer to this question is not that obvious. It's not that simple. And I'll illustrate why it's not obvious with an example. With this specific case. You just left some milk, a glass of milk, in the kitchen before got it, and it's going bad. Okay, so why is it going bad? Because in the milk there are bacteria, and the bacteria secrete some enzymes. The enzymes break down the sugars, and bacteria uptake that sugar. It's a collective effort, it's a cooperative effort. Bacteria work together. They work together to produce these enzymes, but in the end, they all benefit. Now, but think about what's going to happen if one of the bacteria mutates and it's no longer producing the enzyme. Oh, somehow I don't feel like working today. Slightly lazy bacteria. Now that bacteria, since it's not producing the enzymes, is able to grow a little bit faster, is able to reproduce a little bit faster than its peers. And you wait for a little bit, and eventually you see that the whole population is dominated by that little cheater guy, right? Because he's able to reproduce a little bit faster than everyone else. But then what's going to happen? Okay, so they're all cheating a little bit, and no one is producing the enzymes necessary to digest the milk anymore. And this is called the tragedy of commons. The whole colony dies. So there's a cheater, the cheater spreads, now everyone is a cheater, there's no one to freeload, free ride, and then the whole thing just collapses. They all die. We have a similar situation in our own bodies. Okay, so evolution, we always think about, oh, millions of years, dinosaurs, monkeys, whatever, but evolution actually takes place in your body, and we call it cancer. So cancer is just a new species that forms in your stomach lining. It's a lot more fit. It can survive a lot better in that environment, and it doesn't care about the rest, and it just spreads. It's just very fit, It's bad for you. It spreads. It kills you. So it's exactly the situation going on. You have your body is a cooperative effort, and there's one cheater. It spreads, and then everything is dead. Okay, so we're interested in understanding how cooperation, good social behavior, can prevail despite this incentive of the cheaters to take over. Okay, so what we do is we model this, again, in the computer, our little universe. And of course, you need some assumptions, you need some laws. You need to program these laws in your computer. So what we assume is physics of fluids. Okay, we know how that works very well. The equations governing fluid dynamics. Number two, we assume that microbes are little points. And these little points secrete things. And we assume that they secrete two things. One, we call it public good. It's like that enzymes that the bacteria secrete. Okay, so it has a cost, but it's good for the community. The bacteria secrete these public goods. They also produce waste. And it's kind of like your wine bottle. Okay, so why doesn't the alcohol in the wine continue increasing? Well, because it's too much bacteria poop. They can't grow anymore. Okay. So anyway, my bacteria in the computer also produce computer digital poop. Okay? And assumption number three is if I'm a bacteria and the region that I live, if there's lots of public good, I divide, I'm happy, I grow. If there's lots of waste, I die. These are the laws of my little universe. And there are equations, very complicated equations that go with all of this, but I'm not going to show them here. I'm going to show you pretty videos instead. On the left is what happens when the waste molecule, the bacteria poop, is a small molecule and it diffuses further away compared to the goodies, compared to the good molecules. Okay? Now, the green dots here are bacteria. The green dots are bacteria. The red is the public good. The blue is the waste. Okay? So, in the first video on the left, as you can see, it's better to spread out for the bacteria, right? Because if you're hanging out with other bacteria here, there's too much waste. The goods sort of travel further away. So you also want to be further away from the other bacteria. So then everyone is just spreading as far as they can. In the second case, it's exactly the same rules. The only difference is that the waste molecule is smaller compared to the public good molecule, so it travels a little bit further away. It diffuses around faster. And when that happens, it's more advantageous for the bacteria to huddle together to form these groups. See? So and these groups are separated by a wall of waste. That's the blue. So you see a very different structure forming just because of the molecular weights being different, just because of the diffusivity of the molecules being different. So you can think of the left side as like, okay, globalization, big world, and the right side is like everyone has their little villages. Okay, now what is going to happen if I turn on mutations? Okay, now there's going to be some individuals who cheat. They're not secreting the goodies anymore. And then they spread, and then whoopsie, they kill the whole group. They spread, and whoopsie, they kill the whole group. They spread, and whoopsie, everyone's dead. Okay, so you had these little villages, these little cooperative groups of bacteria. You had the cheater mutant emerge in one of them, spread, and killed that group. And then this happened in every group. Eventually, everyone is dead. Exactly what I mentioned before with the milk. Now, let's see what happens if I introduce some flow. Now, I'm going to put these bacteria in some water, and I'm going to turn on the flow. In my little synthetic universe, I remember assumption number one, I put in the laws of fluid dynamics. So I'm putting some fluid. And what's going to happen now is there's this thing called shear. Shear means this, doing this, right? Now, in a flowing fluid, every point on the surface of the fluid has a different velocity. Okay, so if there's a slow region here, and if there's a fast region here, it does this. When it does this, the bacterial groups are torn apart. They fragment. And when they fragment, something very interesting happens. When they fragment, okay, let's say here's a group, it's fragmenting, and boom, there's two groups now. And in this group, there's a cheater, let's say, and it took over the entire group. And whoops, the whole group is dead. But that's okay, right? We still have this. And now this is fragmenting. Whoop, it's split into two groups. And one of them now has a cheater. It takes over, kills the whole group. But that's okay, we have still this. So if the fragmentation rate is fast enough, you can maintain cooperation. You can actually fight against this emergence of cheaters. This is how that looks like. So you don't see it, but there's flow. You know, the top part is going forward, and the bottom part is going backward. So you have this shear. And you can see occasionally that groups vanish because cheaters take over, but still, on the long run, they can increase their number. Okay, so can we do anything useful with this? Could we perhaps do evolutionary engineering? Could we manipulate evolution according to our will and say, well, you know, these bacteria make me sick, and they make me sick like really bad because they're cooperating. Cooperation makes them stronger. So can I perhaps pull a few strings and have these cheaters take them over so that I don't get sick? Can I do something like that? Or maybe I want to go for the opposite effect. So in my gut, there are lots of microbes, and in my gut, I want a certain microbial diversity. I want them to cooperate. Or in a wastewater treatment center, people use bacterial sludges to clean the water. In that case, I want them to cooperate and do their job. So can I actually do evolutionary engineering? Can I strengthen cooperation? Can I strengthen cheaters, depending on the situation? And evolutionary engineering is an old thing. We evolved horses by selecting them, not natural selection, but artificial selection. We evolved bananas. They didn't used to be that great. They were yucky. They had big seeds in them. And you had to cook them. Okay, so one thing you can do is you can use different flow patterns, and you can localize cooperation. So on the left is a flow through a pipe, and on the right is a vortex. Now, there's more shear, I'm talking about the pipe right now, there's more shear at the edges, near the boundaries of the pipe, and since there's more shear, you're going to see that the cooperation prevails near the boundaries, and you'll also see that everyone dies at the center. So I can say, okay, I want cooperation here, but not there. Likewise, in a vortex, there's very high shear along a ring, and not too much in the center, and not too much outside. So you can say, okay, this is the region where I want cooperation to exist, and this is the region where I want everyone else to die. So by adjusting the flow patterns, you can control evolution. You can actually also introduce some chemicals from outside. Okay, so look at the situation at the left. What I do is I add free goodies, free lunch for the bacteria. Now, what happens when I give them free lunch? What happens is that cheaters do take over, yeah, and despite them taking over, they don't die. Why? Why don't they die? Because I'm giving them free lunch. Even though they're cheating, I'm still providing for them. And they're all over the place. And then what can I do once the cheaters are all over the place? I can just stop giving the free lunch, and then boom, they're all dead. On the right, I do the opposite. Now I add some toxins. When I add toxins, even the slightest cheater is going to compromise the fitness of the group, right? They actually have to work really hard now to cooperate because I'm giving them a hard time. Okay, so actually, adding toxins enhances cooperation, social behavior. And these fancy plots, but the point is that I can precisely control how much toxins I give and how much goods I give, and I can precisely control the evolutionary, the social structure of these microbes. And this one is a fun one. I can apply the toxins and goods together in pulses. I apply the toxins and the groups are fragmented. I almost destroy them, but not really. And then soon after I give the goodies, and then they regrow. I destroy them, I give them free lunch. I destroy them, so basically I'm just making them fall apart, and every piece becomes a new group. Okay, so, and fragmentation is good. These little pieces are good, right? Because now the cheaters cannot spread as well. So this works really well. The blue curve is when I apply the pulses. The red one is when I apply no pulses, so I can dynamically control. Another fun thing we do is we look at the evolution of specialization. Okay, so when you look at in ant colony, for example, there's the queen, there's the workers. When you look at humans, there are firefighters and lawyers. When you look at, I don't know. So when you look at your own body, there's brain, there's intestine, you have different components serving different functions. Okay, so the question is, how did this happen? How do you start with a puddle of bacteria, and then you wait for a long time, and then you see, okay, lawyers and firefighters. How does that work? So lawyers are very complicated, and firefighters. So what we look at instead is the simplest possible, like the dumbest possible thing you can look at. Just little circles secreting smaller circles. And we allow them this time to secrete not one thing. Remember last time they were secreting a public good and waste. Now they get to secrete public good number 1, public good number 2, and waste. Okay, so the public goods are the yellow and the red. There are 2 kinds of molecules and waste. So something fun happens. Remember the cheaters in the previous simulations? So now you still have cheaters, but you can be a cheater in a different way. You can be a cheater who doesn't secrete the red stuff, or you can be a cheater that doesn't secrete the yellow stuff. And if you're in the same village, those 2 kinds of cheaters are still going to be able to sustain each other, right? They're not going to die away, because they still have the red stuff and the yellow stuff. They're just half cheaters, basically. And that's specialization. Everyone is doing their own job. And there's also generalists. There are still people doing both red and yellow at the same time. Okay, so there are these evolutionary transitions. I drew them here. These are the possible things that can happen. So you can start with the generalist. These are the green guys. You can transition, and then you can have groups that contain reds and yellows. You can contain groups consisting of only reds and only yellows. Okay, it's like a bunch of doctors here, a bunch of lawyers here. And then those guys are going to transition even further down. You're going to have actual cheaters, right? People who don't do anything at all. And then, of course, those groups are going to die. And we look at two different kinds of scenarios. Okay, it gets complicated quickly. But you can look at a situation where you need both the red and the yellow. Okay, so that's like food and water, right? You can't live without either one of them. And we call that and. Or we can have an or situation. So, for example, peanuts and cashews. They're both very good, and I'm happy when I have both of them. But I can live with just one of them also. It's kind of like that. That one we call or. Now in the and case, of course, you need mixed specialists, right? Within a group, you need people who produce both kinds of things. In the or case, you can have these mixed groups, but you can also have these pure groups. They can survive with just one type. Okay, so I'm not going to go too much into detail about how these things turn out, but you can actually run the simulations and you can see under which condition what happens. So on the left side you have these mixed groups, okay, kind of like lawyers and doctors. And on the right you have these pure groups, purely yellow, purely red. And you can look at different regimes. Different things happen under different conditions, and we can relate them actually. Okay, if you have shear, if the secretion cost is high, or if the diffusion constants are low, if, I don't know, there are certain physical laws that gives rise to different structures, and we classify them and we categorize them, and we say, okay, if these physical conditions hold, then specialization happens. If these physical conditions hold, then generalism is going to be more prevalent. If these conditions hold, then you're going to have, okay, cheaters still sneaking in and coexisting with everyone else, and so on. We classify and categorize. Now, this one is very fun. You get kin selection after this. What does it mean, kin selection? I think the best summary will be with a quote by Haldane. I would willingly die for 2 brothers or 8 cousins. Okay, so you favor your own kids, of course. You love them a little bit more than everybody else. Not a little bit, a lot more. You love your brothers and sisters. You love your mom and dad. There's a reason for that. You share the same genes. That's kin selection. Curiously, we see kin selection in these little stupid circles, bacteria. What happens is we say, okay, look, what if you still have 2 goods, red and yellow maybe, but let's say they have different diffusion constants. Let's say one of them travels far, and one of them is sort of heavy, doesn't travel very far. Which one are the bacteria going to not secrete, do you think? So what kind of cheaters are you going to see more often? Would you rather cheat by not secreting the stuff that goes very nearby? Or would you rather cheat by not secreting the things that go all over the place? Any thoughts? You said something? What's that? You'd rather not secrete the one that goes everywhere. You say, why do you say that? Yes, exactly. So if you stop secreting the thing that goes very close, well, who are you really cheating? Your own brothers and sisters and sons and daughters, right? And who are you killing? Well, other cheaters like yourself. So that doesn't stick. The property of not secreting something that goes very nearby doesn't go very far. But if you cheat by not secreting the thing that goes far away, okay, you're harming sort of everyone, but not particularly your own kin. Okay, so this is what this plot shows. You increase the diffusion length of one of the substances, one of the goods, and the longer it goes, the less you secrete, basically. So it's a manifestation of kin selection on a very mechanical, on a very physical level. Okay, well that's about it. Just to summarize, a computer, or oftentimes for our group, just pencil and paper, is that you can view it as a little universe where you can try out different laws and see what comes out, and you learn things about our own universe. We can set up laws that lead to life and evolving life, and those laws are actually quite simple. You don't really need quantum mechanics and lots of fancy string theory. You don't need those. Just 3 lines, just very simple statements give rise to self-replication and evolution. And finally, in our case, mechanical laws lead to social behavior. You can start with a very physical picture, like, okay, there's a molecule, it diffuses, it flows, these mechanical things happen, you wait for a while, and then you get cheating, and social behavior, and goodness, and loving your daughter, whatever. Okay, all of these comes from molecules. Thank you very much. This work was done by my student mostly.